The title of our paper is Revisiting the Stack-Based Inverse Tone Mapping. The authors are from Peking University, Hefei University of Technology, and Cheng Laboratory. Inverse tone mapping aims to reconstruct high dynamic range (HDR) image from a single low dynamic range (LDR) image by estimating the multi-exposure stack. The generated HDR image also restores the lost textures in the overexposed and underexposed regions of the input LDR image. The main contributions of the proposed method are, firstly, only need to estimate two multi-exposure image. Secondly, bridging the up and down model by the cross-model attention. Thirdly, introducing a learning-based fusion model. The proposed method can estimate more concise and accurate multi-exposure stack and generate HDR images with higher quality. The process of the previous stack-based IDM methods can be roughly summarized in the following three main steps. 1. Training an up exposure model and a down exposure model separately and independently. 2. Generating a fixed number of exposure-adjusted images, example, 3 up exposure and 3 down exposure images, with the trained models. 3. Merging these images by a classic multi-exposure fusion approach. However, each of these three steps has limitations that may cause inaccurate results. Specifically, 1. The process of increasing and decreasing the exposure should not be independent. For instance, when decreasing the exposure, some useful information of the underexposed regions may become subtle, while the features in the opposite increasing process can compensate for it. 2. The times of exposure adjustment are important to the quality of reconstructed HDR images, and a fixed length of MES will cause incomplete information recovery or introduce an unnecessary computational cost. 3. The classic MEF approaches cannot be integrated into the entire end-to-end training process. The main challenges is it is hard to determine the length of multi-exposure stack. The influences of different stack lengths demonstrate that the stack length is important to the quality of reconstructed HDR image. However, the previous IDM methods simply set a fixed length, which cannot be the optimal choice for every scene. Meanwhile, more multi-exposure images will introduce more inference time of exposure adjustment model and exposure fusion algorithm. This image shows the pipeline of the proposed method, which only estimates two exposure images with optimal exposure adjustment, adds the cross-model attention block to bridge the up and down exposure model, introduces the learning-based fusion model to make the whole pipeline can be trained end-to-end. The exposure adjustment model is designed based on the U-shaped model. The previous stack-based methods only need to learn the relative changes between each exposure value, which is easier for the model to predict. However, in the proposed pipeline, the luminance and contrast distributions of the input LDR images are different, which leads to a wide variation in the levels of the ground truth exposures. The commonly used network architecture, such as UNet, cannot handle this wide variation, whose weights of convolution kernel are fixed after being trained. In this paper, we design the exposure adaptive block to extract the high-level and global information of the input image, such as the overall luminance distribution, the scene information, and semantic features. Then we remap the features of the decoder according to the extracted features. In this way, we extract the global features of the input image and use it to control the strength of exposure adjustment to achieve adaptive exposure adjustment. We design the multi-scale dilated convolution and spatial temporal attention mechanism to extract useful information from the reference features, which is called the cross-model attention block. Instead of directly learning the pixel-to-pixel mapping from the multi-exposure images to HDR image, the proposed multi-exposure fusion model predicts the masks to combine the LDR images to one image and then estimate the nonlinear curve to map it to the HDR domain. The experimental results on several public test datasets demonstrates that the proposed method can estimate more accurate HDR results compared to the previous IDM methods. The HDR CNN and deep mask may cause overbright images because of the use of a fixed camera response function. The DRTMO introduces checkerboard artifacts due to the deconvolution. The deep recursive HDRI is easy to blur the images. The deep single HDRI and deep HDR-UNet introduce halo artifacts in the overexposed regions, and the deep synth HDRI fails to reconstruct the correct luminance distribution. On the contrary, the proposed method can recover pleasure results both in the under- and overexposed areas. In this paper, we propose a novel inverse tone mapping method that only needs to estimate two exposure images, i.e., one exposure up and one exposure down, solving the problem that the optimal length of the multi-exposure stack is difficult to be determined. At first, we propose and open the CISES dataset, which can provide the optimal exposure adjustment labels for future stack-based IDM works. Secondly, we design the exposure adaptive block, which makes the decoder generate desired results based on the different luminance distributions of the inputs. Thirdly, we devise the cross-model attention block to utilize the information from both of the exposure adjustment models. Finally, we design the learning-based multi-exposure fusion model to produce more accurate HDR radiance fast. Experimental results show that the proposed IDM method can outperform the state-of-the-art IDM methods in both quantitative and qualitative evaluations.